Hey everyone! In this video, I want to continue taking a look at some indeterminate forms and how we can find the limit of functions that are in one of these forms. So in this video, the indeterminate forms we're going to be taking a look at are 0 to the 0 power, 1 to the infinity power, or infinity to the 0 power. In each case, these are indeterminate forms, meaning we can't evaluate the limit if our function looks like this. So we've already talked in the past about how we can use L'Hopital's rule to help us find the limit of something that's in an indeterminate form. Functions that have this type of indeterminate form, we actually can't use L'Hopital's rule. So instead, we're going to approach it a little bit different. So in general, what we're going to be looking at is we're going to want to find the limit as x approaches some number. And then we have a function raised to an exponent. So I'm going to say f of x to the g of x power. To help us find this limit, if it's in one of these three indeterminate forms, we're going to use the natural log. So I'm going to say y is equal to f of x to the g of x power. And then I'm going to take the natural log of both sides. So you have the natural log of y, and that's equal to the natural log of the right-hand side of my equation. Now, taking the natural log, we can use all the properties of logarithms to help us out. So the power rule for logarithms, if I have the natural log as something raised to a power, I can take that exponent and I can bring it down out front. So this is equal to the natural log of y is equal to g of x times the natural log of f of x. So now we got rid of that exponent, which would hopefully also get rid of that indeterminate form, and now we should be able to find the limit. So we want to find the limit as x approaches c, and we're going to take a look at the limit of the natural log of y. So if this is equal to some number L, then using our properties of logarithms again, then our original limit, so the limit as x approaches c of our original function, so y was our original f of x to the g of x power, this is going to be equal to e to whatever that number is. So I can rearrange using the logarithm, I can find that limit, and then we can undo that rearranging by finding the limit of y, which is going to be equal to e to that number. So let's take a look at a specific example, and hopefully this will make a little bit more sense. So my first example, I have the limit as x approaches 0 from the right of x to the x power. Again, if I try to plug in 0 right away, I would end up with 0 to the 0, which is an indeterminate form, and we can't evaluate that limit. So instead, we're going to think about it as y is equal to x to the x power. And then we're going to use the natural log to help us evaluate this. So taking the natural log of both sides, we can take that exponent, we can bring it down front. So the x will come down, so the natural log of y is equal to x times the natural log of x. So now we want to take a look at the limit as x approaches 0 from the right of the natural log of y, which is the limit as x approaches 0 from the right of x times the natural log of x. So now this limit is something that we can evaluate. If I had to try to plug in 0, I would end up with an indeterminate form, but we do have ways of handling that. In this case, I would have to rewrite this as the natural log of x over 1 over x, and then we can use L'Hopital's rule. But we actually already did that in a previous video, and we know that this limit, as x approaches 0 from the right, of x times the natural log of x, that is equal to 0. So if the limit of the natural log of y is equal to 0, using our procedure we just outlined, then our limit of y, so the limit as x approaches 0 from the right of y is going to be equal to e to the 0 power. e to the 0 power is going to simplify to 1. Y was our original function, so that means all the way up here at the top, the limit as x approaches 0 from the right of x to the x power, this is equal to 1. So we were able to use the natural log to help us evaluate the limit. The natural log, we can do a little bit of rearranging, get our function into a position where we can evaluate the limit, and then we kind of undo that rearranging to give us our actual limit for our original function. So let's talk through that process one more time. My second example, the limit as x approaches 0 from the right of 1 plus x to the 1 over x power. So again, if I were to try to plug in 0 here, I'd have 1 plus 0, so that's 1, and then in the exponent we'd have 1 over 0. 1 over 0, we know that becomes unbounded, so this is an indeterminate form of 1 to the infinity power. So again, we're going to need to use the natural log to help us out. So I'm going to write this as y is equal to 1 plus x raised to the 1 over x power. And then we're going to take the natural log of both sides. After we take the natural log, we can use the properties of logarithms and bring that exponent down out front. So we end up with the natural log of y is equal to, and then I'm going to write this as the natural log of 1 plus x all over x. So now let's take a look at the limit as x approaches 0 from the right of the natural log of y, which means we want to take a look at the limit of this expression, the natural log of 1 plus x all over x. All right, now taking a look at this, if I try to evaluate by just plugging in 0, I would end up with the natural log of 1 over 0. The natural log of 1 is 0, so we still have an indeterminate form of 0 over 0. But now we can actually use L'Hopital's rule. So we want to find the derivative of the numerator and the denominator. So the derivative of the natural log of 1 plus x, this is going to be equal to 1 over 1 plus x. I would have to use the chain rule, but the derivative of the inside is just equal to 1. And the derivative of the denominator, the derivative of x, is just equal to 1. So now our limit is going to be the limit as x approaches 0 from the right of 1 over 1 plus x, and then our denominator here would be over 1, but I'm not going to write that. So now we don't have an indeterminate form anymore. I can plug in 0. We get 1 over 1, so this limit is equal to 1. So if this limit is equal to 1, that means that the limit of the natural log of y is equal to 1, which means the limit of our original function, so the limit of y, undoing our rearranging, would be e to the first power. So that means all the way back here in the beginning, our original function was what we started with, so this limit is equal to e. So a little bit different using a combination of some of our other rules. We can use the natural log to help us find the limit of indeterminate forms. It allows us to do some rearranging. In this case, we also had to use L'Hopital's rule, but in a combination of those, we were able to find this limit and evaluate it to just e.